name's Lucas. I'm a senior product owner at Booking.com, so I don't work for Microsoft, I'm the odd one out. For reference, Booking.com is an e-commerce company. They're not very well known in the US especially, which is kind of odd because we're one of the largest e-commerce companies on the web, so we're very much the hippo or elephant in the e-commerce space. We run more than 1,000 controlled experiments concurrently at any given time. So just like with Bing, if you visit our website, you are not seeing the Booking.com, you're seeing one of the many million different versions. And my team is responsible for the infrastructure that allows us to do that. It allows us to run these experiments, but also the training to help people understand what they're actually doing. One of the challenges, I think, culturally is that we can bring people on board. We're actively hiring and we try to find the smartest minds, but A/B testing is not really done very much outside of some companies that really get it. And so we really have to work hard to, when we get people on board, teach them what A/B testing is and how to interpret the results. So now, in the next 25 minutes, I'll try to do the full day training that I do at Booking in 20 minutes. So that's going to be tricky. I'll try. And for those who have attended the morning session, you will see a lot of things that you've seen before, probably explained a little bit differently. So I apologize for any overlap. The first thing that's very important to understand is that what we're trying to do with A/B testing is causal inference. Like Ronnie said, once we have a correlation, that doesn't necessarily mean we have causation. And the classic example I use is that in Amsterdam, where Booking.com is located, if I look out my office window, I often notice that when people carry umbrellas, very soon after it starts to rain. And so I might conclude that it's the umbrellas that are causing the rain. So I will suggest a treatment or a potential solution to this, and that is that we will ban umbrellas. Now obviously some of you are laughing because you understand that this is ridiculous. But as Ronnie showed, it's not often as obvious in which direction the causal effect lies, even if we have a correlation. And the key thing to understand is that for decision making per se, so for making decisions about a product, getting the causality wrong often results in a worse outcome. So in this case, if I were to ban umbrellas, it will not do anything, it will actually make things worse, because more people will get wet because they're now no longer carrying umbrellas. And so what we're trying to do is causal inference. And to explain what causal inference is, I'm going to use something that's called the Rubin causal model. Mr. Donald Rubin came up with this in the 80s. And what it essentially says is that imagine we have a list of all the people in our population, so all the people on the planet who want to book a room. And then we measure how likely they are to buy our product or click on a link if we show them the A variant of our website. So that's the under A column. These are all probabilities. And then we measure also what the probability is to buy a product under B. So again, we have a second column with the probabilities. And then we calculate the difference between them. We call this the treatment effect, that's the last column. This is the causal effect that our treatment has on each individual. And from that we compute an average, here all the way in the bottom right, called the average treatment effect. And this is essentially what we're after. We want to know if our treatment, on average, for all the people in the population, has an effect. Now, there are three problems, and this Rubin called this the fundamental problem of causal inference. There's three problems in this case. One is that we cannot sample the entire population. There was a question about this in the morning session. In some cases, you actually can sample the entire population, but for a website like ours, we cannot. We cannot include every single person on the planet in our experiment. The second is that we cannot expose units to both treatment and control exclusively. So we could show them A, or we could show them B, but we cannot show them A alone and B alone, right? We have to show them one or the other. And then the third is that we cannot directly measure the underlying probabilities. So in the table I showed you that under A, someone had a 30% probability of buying or clicking. In practice, we will only see whether this person buys or clicks. Now this means that the table I showed you earlier is the underlying truth, but what in fact we can measure, it looks something more like this. We showed Alice A, and she clicked on the link. We showed Bob A, and he clicked on the link. We showed B, got my variants mixed up. We showed Charlie A, and he did click on the link, and Dave did not. Right? So we don't actually observe the underlying probabilities. We don't observe values for both base and variant for individual subjects, and that means we cannot compute these treatment effects in the rightmost column, and if we can't compute the treatment effects, then we cannot compute the average treatment effect, and so we don't get what we want. This is the fundamental problem that we're trying to solve. Now, how do we solve this? One more thing. Because this is a randomized controlled trial, it's a A/B test. Every time we run the trial, we flip coins to assign people to either A or B, and that means that every time we run the trial, we could potentially get different results, because in some cases Alice is assigned to A, in some cases she's assigned to B, in some cases she clicks, and other cases she does not. And so the fundamental problem of causal inference is that we cannot actually measure the underlying things that we want to measure, and as a result we have to fall back to this mechanism to see what we can measure, and this has random variation in it. Now, two key questions that we try to answer with these A/B tests, let me move the mouse out of the way. Two key questions we'll try to answer. The first one being, is there a causal effect? And the other one, what is the size of this causal effect? For most experiments, we're mostly interested in the first question. We want to know, does this thing actually make a difference? And so that's what I'll focus on for the rest of the talk. Now, we're going to use a concept that's called expectation. And so the answer to this question that we will come up with this technique is correct in expectation. And it says that if we show A and B to random samples of a population, so we randomly sample people, and then we flip coins to decide whether they see A or they see B, then the fraction of yes in both groups converges to the true underlying mean. So in A, people have some mean probability of clicking on the link. If we take all the yeses, we count them, and we divide over the total number of people, if you have enough of them, it will converge on the underlying probability. And the difference between these two means converges on the average treatment effect itself. And so the magic of this technique, and the reason that we use statistics here, is that if you take the outcome of what we can measure, and then you compute the fraction here and the fraction here, so this is no, no, yes, so that's 33%. This is yes, 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 so that's 100%. And if we compute the difference, we will get something that in expectation will converge on the average treatment effect. As you saw earlier, the underlying truth here is that the average treatment effect is 0.5, so we actually didn't get the correct number. We got 0.7, but keep in mind that this is only 6 people, so I could have made a bigger table, but then it wouldn't fit on the screen. But since this is a randomized control trial, if I run it again, I will actually get a different answer. Quick note about this presentation, all of these simulations are actually random. If you've opened them up on your laptop, you will get different numbers because it's random. And I also don't know what's going to happen in some of these cases, because that's what random means. So if I'm surprised, don't be surprised. If you run this many times, then the average treatment effect here on the bottom right will also vary, because every time we flip the coin, every time we randomly assign, we'll get this slightly different answer. And so one question that immediately comes to mind is, well, how different? What sort of range of numbers can we expect to see in a test like this? And so what I'm going to do is I'm going to do the same thing that I did before, but instead of 6 people, I'm going to use 1,000 people. And instead of a treatment effect of 0.5, I will use a treatment effect of 0.1. And then I'll repeat this experiment many, many, many times. And on this horizontal axis, we go from minus 0.2 to plus 0.2. And I will plot where the values lie. So imagine we ran this experiment once. The value we got was, and again, I don't know the answer either, 0.121. So assuming that the underlying treatment effect was actually 0.1, this is reasonably close to the average treatment effect. Let's try that again. We run another experiment with exactly the same settings. Oh, that was much closer. And already the average of all of these seems to be moving much closer to the underlying 0.1. So let's do that a lot more times. Sorry for burning your laptop CPU. If you do this a lot more times, you see that you actually get this very nice bell-shaped curve, normal distribution, around the average observed effect, or the average treatment effect. Now, because we're using randomization to assign people to either A or B, we can also say that only 3 things can really explain any difference that we see. So if we run a test once and we observe a difference of, say, 0.121, then only 3 things can really explain any difference we see. There can either be a causal effect, what we're looking for, something in what we did made people click more. There could be pure chance. It might mean that just because of the randomization, some more people that clicked ended up in the B group. Or there's a measurement error. And this is why, what Ronnie mentioned, it's so important to make sure that you trust the underlying infrastructure. Because this third explanation, you never want it to be the actual explanation. Now, we want to reject the null hypothesis. And the null hypothesis in this case assumes that there is no difference between these 2 treatments. We are going to say that the null hypothesis is that pure chance, so the second explanation, is the only reason that we observe any difference between these 2 groups. And if we could reasonably rule out chance, so if we can rule out this null hypothesis, then we might reject it, say this does not explain what we see, and that might be used then as evidence for any alternative explanation. And to do this, we're going to compute a p-value. We assume that the null is true, and we compute a p-value, and this p-value is the probability of seeing a particular result, or more extreme, again, assuming that there is no difference. So how likely is this result, assuming that it's the result of pure chance? Now, to give you some idea or some idea of what intuition you already have about this, let's play a little game. I programmed a die, a normal 6-sided die. I'm going to roll it, and I'm going to ask you if you think this die is a fair die. Yeah? So I roll it once, and I get a 6. I mean, could be lucky, right? Anyone still willing to believe that I just got lucky? Seems like a reasonable explanation. So let's roll it again. Again, this is a live simulation, so I have no idea what's going to happen. I roll it again, and it's another 6. Who's starting to question this particular die? Paul in the back already? Yes? Okay, one more time. Let's roll it one more time and see what we get. Another 6. Okay, so who now still believes that I didn't cheat? No one. Or no one wants to raise their hand. And the probability of this happening by chance, so if this die were fair, then the probability of this happening is 0.46%. It's very small. And to answer your question, it's not fair. I totally cheated on this one. And this die will always give us a 6. And so the p-value is useful because it tells you a probability for this thing that you intuitively already feel, right? You already feel that this is very unlikely to happen. Now, what we need to do in order to reject the null is to pick a threshold. We need to decide when are we going to reject this thing. And one swallow doesn't make a summer, nor one fine day, but essentially we have to decide how many swallows do we count before we pack up our umbrellas? How long before we decide that this thing is not due to chance? And the scientific standard here is 0.05. So you would reject the null if the result you see is less likely than 5% to happen by chance. Now, 2 die coming up as 6 already meets this threshold. So this threshold is not really that strict. As Ronnie said, when you have enough samples, you can actually put a much stricter threshold on this. P-values are often misinterpreted. Ronnie already talked about that. I would just recommend you read Steve Goodman's paper. I'm not sure how I'm doing on time. I want to spend a bit more time talking about the actual errors we can make, because I think that's much more important. There are 2 types of errors that we can make when running experiments like this. The first one is a type 1. That is the incorrect rejection of a true null. So if there is no effect, we might say that the data we see is very unlikely to happen. It can still happen. It is possible to throw 2 die and get 2 6s, but we would reject the null because it seems so unlikely. The story I usually use to explain this is the story of the boy who cried wolf. Is there anyone who doesn't know the story of the boy who cried wolf?
I'm willing to admit it.
and willing to admit it? Okay, so there are a few people. So the story of the boy who cried wolf is the story of a young boy living in the Austrian Alps. Let's call him Hans. Any Hanses in the room? Just to be sure? Okay. It doesn't end happily. Hans is a young boy living in the Austrian mountains, and his mother says it's time for you to get a job, and I've already picked a job for you. You are going to go up the mountain and tend the sheep. So tomorrow morning you are going to go up and then sit while the sheep graze, and if a wolf shows up, you're going to cry wolf. Fair enough, thinks Hans, that sounds easy. And so the next morning he gets up, has his breakfast, walks up the mountain, and sure enough, the sheep start grazing and Hans sits down on a rock. Now this is in ancient times, so there were no iPhones, no iPods, no Game Boys, no nothing. So after a few hours, Hans gets super bored. And what does a boy do when he's bored? He starts to daydream. And he comes up with an amazing plan. He says, you know what? If I were to cry wolf, then all of the people in the village would come up and we could play a game, like hide and seek or something like this. And so Hans cries wolf, wolf. And all the people in the village, they hear the signal, wolf. And they conclude, there must be a wolf. And so they drop their stuff, run up the mountain, and find no wolf. Hans, of course, gets a nice beating from his mother. Don't ever do that again. But you get one more chance. So next day, Hans goes up the mountain again, tends the sheep, sits on his rock. About a few hours in, again, no iPhone, no Game Boy. He's again super bored. And so he starts to daydream again. But this time, because he's daydreaming, he doesn't realize that right behind him, a wolf has snuck up. And before he has a chance to scream, the wolf eats him whole. This is why I asked for no Hanses. Now, down in the village, the people are conscious that this is about the time of day that Hans cried yesterday. And so they perk their ears, they listen, and they hear nothing. And because they hear nothing, they conclude that therefore there is no wolf. Now, the first day, when Hans cried and there was no wolf, the people in the village made what is called a type 1 error, or they concluded that there was a wolf because there was a signal, but in fact they were wrong. Now, the second day they make what is called a type 2 error, which is when we conclude there is no effect because we don't find a statistically significant result. Let's try and generate some type 1 errors. So in this case, I'm using the same simulation I've used before. Again, 1,000 people, but this time I'm simulating an actual effect of 0, which means that previously the bell curve was circled around here. And if I do this, I would expect to get more results centered around 0. But because the simulation is random, sometimes I flip the coins in such a way that we get a result that is so far away from 0 on either ends that we reject the null. We say, no, this can't be due to chance. This is 3 6s in a row. What do you think? That is fair? And so in those cases, we are incorrectly rejecting the null because we are still simulating no effect. And as a result, the type error rate here is about 5%. Now, the type 2 error rate, which is concluding there is no effect because the result is not statistically significant, I can also simulate. If I simulate a smaller effect than I did the first time, so half of that, but non-zero, I get a normal distribution which is somewhere between the previous two. And in this case, the lighter blue here being non-significant, the dark blue being significant, we can see that in about 33% of the cases, we conclude there is no effect when in fact there is. Now, the thing that drives this second error is a concept called statistical power. And statistical power is the probability that a test correctly rejects the null if there is indeed an effect. And there's two main things that really affect it. One is the sample size. So if we get more people, then we're more likely to correctly reject the null. And this is why the theory says that assuming that the null is never really true, if you just get enough people into your experiment, at some point you will be able to reject it. And that's true if you have essentially infinite sample size, but again, at some point you run out of humans. And the other thing that affects is effect size, and that's why Ronnie says, but we're looking for very small effects. So if effect size goes down, sample size must go up to correct for it. And I can fix the 33, so remember here, we had 33% type 2 error rate. If I find that unacceptable, I can increase my power by saying, let's double the number of people in this experiment. Remember, effect size is exactly the same here, I just doubled the number of people, so power should go up. And as a result, this thing is the worst, observed power is 92%. Now, type 2 error rate is 8%. I could double again, and this is why I'm saying you run out of people. I need to double again to go up to 100%. Power is non-linear, so you need to keep doubling if you want to increase your power. Now, the last thing I want to talk about is the importance of protocol. In the morning session there was some talk about multiple testing, but really what we're talking about here is people violating the assumptions that underlie the method, and that's what we call violations of protocol. The methods assume, so the statistical methods assume that you strictly adhere to the protocol, and things that are quite common, like peaking and multiple testing, essentially violate it. And to give you some intuition for why violating the protocol is a problem, let's take another die. So this is a different die from the one before. And again, we're going to roll it 3 times. And I'm curious if you think that this die is fair. So, yeah, you ready? Okay, so I roll this die. And, wait, no, so I'm sorry, and this is what happens with random simulations. Let me roll it again. Let's roll it just a few times. Yeah, there we go, So who thinks this die is fair? I got 3 6s, right? I mean, essentially I kept rolling the die until I got 3 6s, but I still got 3 6s. So the p-value for this happening, if I keep rolling, is 1. If you keep rolling, at some point you will get 3 6s. There is just no probability that this would not happen if you keep rolling the die. And so this die is actually fair, but I still cheated. I just cheated in a different way. I used a fair die, but I kept rolling it until I got the result that I wanted. And this is essentially what you're doing when you're multiple testing, when you're peaking. You keep repeating the test until you get the result you want. Now we can also simulate this. We're using n equals 1,000, so 1,000 people in the test. The treatment effect is 0, so this should give us a false positive rate of 5%, because that's what the statistics guarantees. But instead of checking only once, as the statistics assumes, I'm going to check 2 times. Only 2 times, I mean, it's not really cheating, right? So let's see what happens. What happens is that if I check 2 times, the type 1 error rate actually goes up to 9%. The tails get much fatter. There are more instances where I incorrectly conclude that this thing has an effect, simply because I peaked more times. I didn't change anything else about the underlying statistics or the math. What I changed was the protocol. Now, the more I change the protocol, the worse this gets. So I'll use the same underlying distributions, I'll use the same math, but I'll peak 100 times. And in the morning session, someone talked about, but we have all these parameters in the model and we test for 50 different values. Well, essentially that's what I'm doing. And what happens is that the type 1 error rate, so the number of false positives, or the times that I incorrectly reject the null, goes up to about 32%. And so just by changing the protocol, I can violate the assumptions under the statistics and draw incorrect conclusions about the presence or not presence of an effect. Now, there are good reasons for violating protocols. So now I'm going to contradict myself, because more flexible protocols are often desirable, especially for product development, but also in medicine, because early stopping rules might help you mitigate damage. If something is really bad, you want to stop it very early. And so you want to keep checking multiple times just to ensure that when it is really bad, you are able to stop it. Early shipping could help you minimize opportunity cost. If you have to wait for a very long time, you could be losing revenue. Multiple variants, as Ronnie suggests, allow you to try different things at the same time. So not just doing A, B, but A, B, C, D, E, F, G. Could be an instance of multiple testing if you do not correct. And then Ronnie mentioned 2,000 metrics. I think for booking it's very similar. Thousands of metrics in the tool for a single test. If you test all of them, then you're essentially doing the same thing as rolling the die again and again and again. All of these are possible, but they do require protocol adjustments. If you stick to the original protocol, but you violate it in the ways that that are written down here, you will inflate your type 1 or your type 2 error, and so you want to make sure that you adjust the protocol to allow for these sort of things without affecting the error. I think that's where I run out of time. Are there any questions? Do I have time for questions? Yeah. I do? Awesome. Are there any questions? Yes?
Yeah, so you're assuming that the change is going to make this normal distribution. What happens when your change makes this bimodal distribution? Like where for some users it's really awesome, but for other users it's really bad, right?
Oh, this is an excellent question. So what if so you're asking what if the underlying effect distribution is not actually a normal distribution? Yeah. The statistics we use don't necessarily require that the underlying distribution is normal. The central limit theorem guarantees that the means are distributed normally, and that's enough. So one thing that could be a problem is when the treatment affects different people differently. And then you have heterogeneous treatment effects. This is something that's considered a big problem in social sciences or medicine. For product improvements per se, so for instance revenue, we're interested in average revenue per user, and we're not really interested in knowing whether that revenue came from one particular part of the audience. And so for those particular cases, we're mostly interested in what is the overall effect this thing will have on our business. Does that make, Ronnie, feel free to disagree. I see Pavel going.
Alex is going to talk about this.
Alice is going to talk about this?
Yeah, I'm going to talk about it.
Alice is going to talk about it.